So we're going to look today at metallic bonding. So let's think if we had a solid piece of pure iron and we were to look really closely at that solid piece of iron, we would see that it's made up of particles. And because it's a solid, these particles are arranged in a regularly arranged lattice. And they're just vibrating on the spot. But let's look actually a little bit more closely at what's happening here. So let's focus in on a little bit more. Let's focus in on just 6 of these particles. So what we'd actually see is the particles were all touching each other, and really importantly, their outer electron shells are all touching each other. So I'm going to show the outer electron shell now by with a dotted line inside. So this dotted line here represents the boundary of the full shell under the outer electron shell. And because it's got the nucleus in it, I'm going to give it each of these a positive charge. And then around here, I'm showing the outer electron shell. And I'm just going to randomly put some electrons into there. So what we've basically got are positive metal ions. And here we've got the outer shell electron. So positive metal ions and the outer shell electron. Now, because these outer shells are all touching, they actually overlap slightly. And rather than having separate metal atoms, the outer electron shells all join together to give us a sea of outer shell electrons. Now we give that sea of outer shell electrons a name, and it's a sea of delocalized electrons. So I'm showing now the positive metal ions, which I'll just relabel here. And then this box around here is representing a sea of delocalized electrons. Now, delocalized means they are no longer moving within a particular outer shell, but they are moving anywhere within this whole structure. And in fact, they can move throughout the entire metal structure. So why is this important? Well, if we think about this, the structure of a metal as being positive metal ions in a sea of delocalized electrons, it allows us to explain 2 things about metals: its electrical conductivity and conductivity of heat, and the relatively high melting points that metals have. So let's write down our structure again. So a metallic structure or metallic lattice is made of positive metal ions in a sea of delocalized electrons. And both of these give us the giant metallic lattice. So it's a regularly arranged structure that goes on infinitely, therefore it's giant, and lattice means it's a regularly arranged structure. So we've got 2 things that we need to know. These delocalized electrons, and I'm just going to write that again, delocalized electrons, as E minus represent electron, can move through the structure. If they can move through the structure, they can carry a current, and they can also carry heat energy or kinetic energy, carry current and heat energy. So as a result of that, metals are good conductors of heat and electricity, or thermal energy and electricity. So that's our first point, that our delocalized electrons, a sea of delocalized electrons, can move through the structure. As a result of that, they can carry a current and also heat energy, and therefore they are good conductors of heat and electricity. The second point that we need to know is that there are strong electrostatic forces. So we've seen electrostatic forces before when we looked at ionic structures, but we've got strong electrostatic forces. And these strong electrostatic forces are between the ions and the delocalized electrons. These require lots of energy to overcome. As a result of that, metals have relatively high melting points. Thank you very much.